first video. Okay, fact. I have a question on homework.
What about the homework?
A few questions that are for warm-up exercises. You expect them to be handed in also?
The warm-up exercises I don't expect to be turned in, but the warm-up exercises are I think, a very good thing to do, because a lot of the exercises are hard. The warm-up exercises are relatively easy. And so it's sort of important to go through them to get ideas and stuff like that. So it's sort of like, you know, doing your stretching if you're exercising. It's important to do the stretching, okay? But you don't have to put it in. Okay? Any questions? Okay. Is that it? The answer to the question or any more?
No, that's it.
Okay, great, thanks. Okay, let's start off now. First of all, are there any questions about projects or homeworks or anything logistical to start us off? Any questions? Okay. Most people by now have come by and spoke with me about projects, which is good. Okay. If you have not turned in a project proposal, turn it in. It doesn't have to be today. It can be next week. Okay. The important thing to me is that you've thought about it enough that you can be convinced, yeah, I know what I can do for a project proposal. You look at your calendar, you say, when am I going to do this? I should figure out the work. Be convinced that you can get your project done, okay, based on what you have started with. And, you know, and get working on it early enough that if you get trapped, you have a chance to change projects if necessary. Some people have picked problems that they may not know what the first step is. They may think they have a first step, but that first step may last for about an hour or two. After you think about it for an hour or two, you may have exhausted that first step and now have no place to go. Okay? So my recommendation is that if you're going to do that, do the thinking about the first hour sometime early in the semester so that you can be pointed to another project before it's due, other than you sort of find yourself trapped the day before the project's due, okay, and you have no place to go. That's a bad feeling, okay, and I want you to avoid that feeling. Any questions? Any questions about homeworks or anything like that? Any questions about what we talked about last class? Last class, we had talked a little bit about about convolutions. We introduced some problems where a counting problem where convolutions came up naturally. That was the spanning trees of fans. What I'd like to talk about today in the 16th lecture of CSE 547, the discrete math class, is another counting series, okay, another combinatorial problem, but one that involves sort of some counting sequences that involve convolutions, okay? And this is one of my favorite sort of counting kind of problems. We've seen the Fibonacci numbers, and they count certain things. We've seen the binomial coefficients, and they count certain things. The Stirling numbers, they count certain things. The Catalan numbers, I think, may well be the last sequence we're going to explicitly define this semester. I don't guarantee that, so don't hold me to that. But the Catalan numbers are a counting sequence that tends to come up over and over because it inherently involves convolutions. Okay? What is the Catalan numbers? Well, we'll see a definition in a few minutes. But basically, the nth Catalan number is the sequence goes sort of 1, 1, 2, 5, 14, 42. Okay, 130, you know, 132. 42 is a good number to remember because that's sort of an unusual number. Okay, if any of you ever read The Hitchhiker's Guide to the Galaxy, you'll know the number 42 appears prominently in that. Okay, if you haven't, it's an interesting book to see why 42 appears in there. But anyway, it's something that when you see it, maybe it'll jar you that the Catalan numbers are where they came in. You know, might be a relevant thing to count. But let's look at a couple of different, seemingly very distinct problems where the Catalan numbers are what really ends up counting it. Okay, and the classic application of the Catalan numbers is in counting how many ways there are to multiply, distinct ways to either parenthesize an expression, or equivalently to think about how many ways there are to multiply out a sequence of n numbers, n plus 1 numbers using n multiplication steps. So what do I mean by this thing? Well, basically what I'm talking about is if you think about a sequence of operations, okay, let's say we have 3 elements. How many ways are there to parenthesize 3 elements such that, in different ways, or to multiply it out? If we put the innermost parentheses, if we have 3 elements here, I claim there's 2 distinct ways to parenthesize it. Okay? One way to do it would be that we have the innermost parenthesis the innermost parenthesis means the thing you do first, right? So this would say that you do x0 times x1 first, and then multiply the outcome by x2, correct? This would be one where you do x1 and x0, and multiply the outer thing by x1, by x0, okay? These are 2 distinct. In multiplication, we know multiplication is commutative and so associative, and so it doesn't matter to the answer. But I'll claim that these are 2 distinct ways you could parenthesize an expression, okay, to multiply it, okay? And there's 2 of them for 3. Is there any other possibility way you could multiply 3 numbers using, you multiply them? Well, you could say I'll multiply this one, the first and the last first. That rearranges things. That's not parenthesizing. That's permuting, okay? So there's only 2 ways to do it for n equals 2. Does everybody agree with that? What about for n equals 3? I mean, for n equals 3, meaning now we have n plus 1 or 4 elements to multiply. I claim that, that there are 5 ways to do it. And the ways to do it are sort of shown out here, okay? You could have the first outermost multiplication, the last one if you want to think of it, be x0 times something else. That something else was a set of 3 numbers that had to be parenthesized, right? And we showed that there were 2 ways of doing that. So I think you'll agree that if we start out with x0, there's only 2 ways to finish the job. Likewise, if the last thing is going to be x3, there's only 2 ways to finish the job, right? Because you've got to parenthesize the 2 things before it properly. Okay? Correct? Because there's only 2 ways to parenthesize 3 objects. Okay? If we insist on the outermost parenthesis, the 4th thing, being last, then any way we could permute the other guys. I think this is missing this is not a well-formed thing. Now it's legal. Okay? So the only other possibility would be that we break it, instead of the outermost thing being there or there, we break it in the middle, and now we're stuck. There's no other possibilities we have. So in fact, there's only one way to parenthesize these guys if we insist on the outermost step being in the middle. Okay? That would give us, a total of 5 ways to do it. Any questions about why there are 5 ways to multiply 4 numbers using 3 multiplications? Okay? Now, in fact, this number I've shown you is actually can be thought of another way to think about it, is to think how many ways are there to form well-formed parenthesizations of, sort of n sets of parentheses. Okay? There's not quite the same thing as that. There's not a direct map. It's not obvious how to go from one of these to one of those. Okay? But here I have what I claim are the 5 distinct ways you could take 3 left parentheses and 3 right parentheses, okay, such that everything is well formed. Okay? What does it mean to be well formed? It means that as you go from left to right, you always have at least as many left parentheses as right parentheses, right? That's what it means to be well formed. If somebody does something like this, this may be looking very well formed. The moment they have something like this, they have more right parentheses and left parentheses, suddenly they got trouble. Okay? If you look at this, you'll see that there's exactly 5 well-formed parenthesizations of 3 sets of parentheses. Okay? So lo and behold, again, it looks like there's a cuddle-on thing coming in. Okay? We need a proof of that. But, again, another example of something being counted by this. Any questions? But let's talk about the number of ways to multiply these numbers out. Okay? When you want to count something, the first thing you do is you give a recurrence. What would be a recurrence to count how many ways there are to multiply the numbers 1 through n plus 1 using, n multiplications? Well, you notice that when I was breaking down the number of cases, I always said that we said, let's look at where the outermost multiplication goes, correct? Okay, in any way to multiply things, okay, here we have our examples again, there is an outermost multiplication, correct? That's the last one that you would be doing. Obviously, the parenthesization somehow specifies an order for what you're going to be doing. If there's an order specified, there has to be a last thing, okay? Let's think about what the last thing does, okay? If we have here 1, 2, 3, 4, 5, 6, n numbers, okay, there are n minus 1 spaces between those n numbers, correct? Actually, that's it has to be short, because this is how we counted. Here we have n plus 1 numbers, because we counted from 0. That meant that there are n plus 1 minus 1, or n spots between the numbers, right? I claim any one of those could be the outermost multiplication, correct? I mean, which one, if not, that means there's one that it couldn't be. If this wanted this to be the outermost multiplication, how do I do it? Well, put a parentheses between here and there, take care of everything in there, and then this is going to be multiplied by that. So there are, all told, n possible places for the outermost multiplication. So let's say that let's have k be the position of that outermost multiplication. How many ways then are there to parenthesize these numbers, to multiply these numbers? Well, once I've decided to put my parentheses, my outermost parentheses here, chunk, 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 I've now got these numbers to finish up and these numbers to finish up, right? I've broken my problem into two problems. Any parenthesization of this coupled with any parenthesization of that gives a distinct parenthesization for the entire thing. Okay? How many people believe that or agree with that? How many people don't agree with that or unclear why that is? Okay? It's the basic counting reason is again this. If I give you, I tell you that there's 56 ways to pick, something from here and 92 ways to pick something from here. How many ways is there to pick one of these and one of those? Well, I can pick 56 times 92, correct? So my claim is the number of parenthesizations on n plus 1 things is, well, if I put the outermost parenthesization here, I've got 0 elements left on one side. Okay, so there's C0 ways of parenthesizing that. I realize there's one element here, but remember we're counting, n is going to be counting the number of spaces between elements. If you've got one element, there's no spaces between them. On the other side, how many elements do we have? Well, there were originally n spots between them. We killed one of those n spots between them, so there's n minus 1 spots on the other side, right? Okay. If we put the first partition here, then what do we have? We have one possible spot on the left and n minus 2 on the right. Why n minus 2? Because we had the one that we just broke with the outermost parenthesization, and everybody else has to be on the other side. In general, I claim the number of parenthesizations on n things is the sum over all k of the number of parenthesizations on k things times the number of parentheses on n minus 1 minus k things. Okay, we sum that up over all possible values of k. Okay, that I claim is a recurrence that counts that. Any questions about that? How people sort of see that recurrence and understand it? Okay, good. This n equals 0 is simply the basis condition. That says that if you've got 0 elements or 0 spaces, you've just got one things, How many ways are there to parenthesize that? We'll say there's one. Okay, that's just the basis case. Okay, any questions?
What K represents again?
What does K? K is going to represent the position of our outermost multiplication. So K could be, starting out over here, we'll number our positions. Suppose we number our positions from 1 to n. Okay? Then K could be 1, 2, 3, 4, up to n. Okay? K is going to represent our counter, describing how we, basically describes how we break it into two parts. K is going to count how many elements, if you want to think, are in the first part. And all the remaining elements are going to be in the second part. Okay? Any questions? Okay? So what does that mean? Well, this is a recurrence. How do we solve this recurrence? Okay, I tell you this recurrence comes up a lot. Why does it come up a lot? Well, one is it does. But there's actually, your bones feel why this recurrence comes up a lot. Okay? It is somehow the simplest kind of recurrence you can form by convolving to a sequence with itself. Okay? So a simple kind of expression, by definition, is going to come up a lot. Okay? Now, let's look at actually now solving this recurrence. Okay, any questions so far? Okay? So this sequence, this is the recurrence for the Catalan numbers. If we want to solve this recurrence relation, there's two ways we can do it. One is by using the generating function techniques. The other is by a combinatorial proof. Okay? Let me first show you just quickly the generating function method to show you that it can be done. Okay? And then I'll show you a counting argument. Okay? Any questions? So how could we solve this recurrence relation? Well, if we're going to use our generating function method, what did we do? Well, we said that Cn is going to be equal to this. We multiply both sides by z to the n. We sum up over everything. We get a recurrence relation that looks something like this. The generating function for the Catalan numbers is going to be equal to the sum over all n, over all k, of ck, cn minus k, times z to the n. Okay? That's because we're multiplying this, each one of these by n, by n. This thing, n equals 0, is only going to be only going to be true at n equals 0, so that's going to be just 1, because all the other terms went away. That should be clear. What happens over here? Well, we can do the same trick that we used last lecture. Okay? We've got a sum here before the sum went over all k. Okay? Such that I guess k was between 1 and n. Here, we now have to sum that up over all n. Okay? Now let's note we have a double sum. Let's put the sum over n in here and the sum over k out here. We can factor out the k. We can factor out z to the k out of the z to the n, okay, if we want. Okay, and what's going to be left in this sum over all n is going to be c to the n minus 1, okay, minus k. By the time I factored out the z to the k, I've got z to the n minus k here. This term in here, since I'm summing up over all possible values of this thing, you see the difference is a difference of 1 between the exponent and the coefficient. That means I'm really summing up over all possible values. This would be the same as z times cz. Okay? The z is going to take care of that shift. If I pull out an extra z, then I have the sum of c to the n minus 1 minus k times z to the n minus 1 minus k. Summing up over all values of n minus 1 minus k, that gives us our closed form generating function. This is what we get as a closed form. Cz equals that plus times z times cz squared plus 1. Any questions? Okay?
Yeah, earlier when you have the recurrence as summation above, you had summation of k.
Yeah?
And then when you got to the next line.
Okay. How do we go from here to here?
Yeah, you got summation of k, comma, n.
Okay, well, what are we doing from here? Here we have a sum. This is over all legal values of k. What are the legal values of k? Well, you could have actually some kind of a test here. But we know that we're going to want c equals 0, k equals 0 is the lowest. Okay, interesting one. And all other values, so long as k is greater than 0, this is summing it up. But since c of a negative number is going to be 0, okay, this is the same as enforcing that k goes from 0 to n, right? Or n minus 1. Okay? In going from here to here, like all the times, we multiply everything by z to the n. We have a sum over all n. So this becomes, we slap an extra summation around here, summing up over all n. That's what this is saying. That's what we did here. We summed up over all n. Okay? Okay? But this, in fact, was going to be true only for n equals 0. So the degenerate case came down to there. Okay? So this became a double sum. Once it became a double sum, we partitioned the terms and did it that way. Okay? Any questions? Okay, good. Now, we know that z times cz squared minus cz plus 1 is a closed form for our generating function. To solve for cz, we can use the quadratic formula. Okay? Because again, cz, it's now a quadratic. Now this starts to look ugly. How do we expand such a thing? Okay? The reason it looks ugly is because it is kind of ugly. Okay? It's one reason. Okay? But how, in principle, would you do it? Well, here you've got two terms. There's a plus and minus term, which you get from the quadratic formula. One of them I claim is right. Okay? I claim the negative term is right. Okay? If you don't believe me, work it out for the positive term. It'll give you something different. Okay? If you take a negative term, now we know that cz is going to be equal to this. Okay? How would we expand this? Well, the critical thing is this thing with the square roots. 1 minus 4z to the square root of it. But we have an identity to somehow deal with this. This is this to the 1/2. This is sort of one of these things where we use the binomial theorem. Okay? And you can expand that to be, by just using the binomial theorem, 1/2 choose k minus 4z to the k. Okay? Times 1 to the k. That's, but when that went away. Okay? Now what could we do with this thing? Well, we could work on it a little bit to this kind of an expression. Okay? And then use an identity to get rid of the fractional binomial coefficient, to replace it by this other coefficient. I think we actually went through this identity, okay, in class before. I don't tend to remember that identity, okay? But once you finish working with the algebra, you can show that the nth Catalan number, in fact, actually has a nice form to it, okay? Through n, choose n over n plus 1, okay? If you grind through the algebra, it's, you can sort of see that this is right. Okay, but this is not the kind of derivation that I would do comfortably. Okay? Any questions? Okay, although at the end you get an interesting number. It's such an interesting number that there should be a proof that is not analytical, okay, but one that is a combinatorial kind of a proof. Okay? And this is a little trickier than some of the other combinatorial proofs. Okay? But I'd like to go through that, because I think this way I can convince you that the nth Catalan number is 2n choose n over n plus 1. Okay? How do we do that? Well, actually, let me hold off on this for 1 second until I show you something else. Okay? I will show you this combinatorial proof, but I think I want to convince you that the Catalan number is some things before that. Okay? Any questions? Okay? So, you now have seen the Catalan numbers. You have seen that I tell a very hand-wavy proof about how large the Catalan numbers are. Let's go back and see why are they interesting. Okay? Let's count the following problem on elections. Okay? Suppose, let's say, we have an election between political election between two people. Okay? Candidate A and candidate B. And the election is going to end in a tie. Okay? And further, but despite that fact, when they count the votes one by one, suppose candidate A was never behind. Okay? It's going to end in a tie. Candidate A is never going to be behind. Okay? Each guy ends up with n votes. How many ways could they have had this kind of an outcome occur? Okay? Let's think about this for a second. Okay? Actually, those of you who are baseball fans will have a more realistic interpretation of this. Remember last year, Mark McGwire and Sammy Sosa, okay? Remember those two people? Home run hitters. Set a new record for the most home runs hit in the season. Does anyone really, how many people are familiar with this event? Yeah, people, okay? If you may remember from the sporting pages, Mark McGwire, at the end of the season, they were the day before the end of the season, they were tied. And yet that entire year, Mark McGwire was always ahead, right? Mark McGwire was never behind Sammy Sosa, okay? And yet they ended up at a tie at one point. That's kind of exactly what we're asking about here. How many ways could such a thing have happened? Okay? Any questions about what the thing is? Another way to think about this kind of an event is to think in terms of paths on a lattice. Okay, I give you an n by n grid. Okay, let's count the votes. Okay, in the following way: anytime Sammy Sosa gets a vote, Mark McGwire gets a vote, we make a line to the left. Anytime Sammy Sosa gets a vote, okay, or a home run, we move up. Okay. What is the property of this path if at the end, okay, they end up with the same number of votes? Okay, or the same number of home runs. My claim is if at the end they end up with they both end up with n home runs, okay, then the starting point was 0, 0. The ending point was nn, correct? Each time Mark hit one, bop, bop, bop. Each time Sammy hit one. I claim that the way that the home runs were distributed, the order at which the home runs were hit, describes a path from 0, 0 to nn. Okay, how many people believe that, understand that? That should be clear. What if we want to insist that Mark McGwire never fell behind? Okay? What property did that path have to have? Okay? My claim, the property is the diagonal line, the line y equals x, is exactly where Mark McGwire and Sammy Sosa are tied, correct? So if Mark McGwire was never behind, the path never went up beyond that. Okay, does everybody agree? So a way to think about what we're counting is, how many paths are there from here to here, from the length n, this is going to be n, and that's n, such that the path never crossed that. Yet the path always moves to the left and to the right. Okay? How many such paths are there as a function of n? Okay? Any ideas? Say factorial. Okay? But factorials have to do with arrangements of things. Okay? I don't see arrangements. I guess I sort of see some arrangements. But the Catalan numbers have factorials in them. Remember, the answer for the factorial, the Catalan numbers is counting. 2n, choose n. There's enough factorials there, okay, for what we're interested in. How many such paths are there? Well, I've sort of told you, it's counted by the Catalan numbers. Why? Well, let's look at it. Suppose we consider a path that starts from here and ends up at a tie point. What do we know? Eventually, that path is going to hit this diagonal line. It would hit at the end, right? At the end, if they end up tied, it'll hit the diagonal line. If Mark McGwire hit all his home runs, then took a vacation and Sammy hit one, they wouldn't hit it more than once. Okay? But as happened in that case, and it will happen quite often, it might bang against that diagonal line a bunch of times, right? let's think about, let's let K be the first place where our path hits the main diagonal. Okay? How many ways are there to have a path that goes from here to here, which never crosses it, which hits that point K as the first point in here to here? It means that the first move had to be a move for Mark McGuire, right? Because there's no way he was ever behind. If we end up here, and we had never had anything that went to the diagonal beforehand, I claim we have a lattice path that starts from here, goes to here, okay, that never goes above that diagonal, right? This dotted diagonal. How many such ways are there to do that? If there are Cn ways to go from here to here and hit that diagonal, then here we've got K minus 1. It's a problem of, this is a problem of size K. Moving in on each side gives us a problem of size K minus 1, right? And now we want to go, so there's a problem of size K minus 1 here. On this side, there's a problem of size what? N minus K. Okay? Any path of size K minus 1 here and N minus K here is legal. I claim that C sub n, the number of paths, is equal to the sum over all possible first hitting points, first tying points, of Ck minus 1, how we got to that tie, times the way we left that tie and ended up tied. Okay? This recurrence has to count that thing. Okay? How many people see the recurrence? How many people don't see the recurrence? A couple people. Good. Okay? What am I going to claim? Any path from here to here, okay, can be described in terms of its first hit to the axis. Does everybody agree with that? That if I give you a path, you could tell me the first point where it's tied, right? Well, let's now count all possible paths. Break them into classes based on where they had their first tie. Okay? How many paths had its first tie here? Well, if it had its first tie here, it meant we know it didn't hit any of these points, right? We know Mark McGuire was always ahead. So the first move had to be this way, right? We know this is the first tie. So the last move up to that tie had to be straight up, right? There's no way we could go into the tie horizontally, because that meant we were already in alien territory. Okay? So how many ways are there to get from here to here? Well, this is exactly a smaller version of the problem, right? It's a problem of size K minus 1. All right? So if there are C to the n ways of doing the whole problem, there are C to the K minus 1, okay, ways of doing this part of the problem. Once we're there now, any lattice path from here to here that is legal, okay, it doesn't go above the line, represents a possible conclusion. How much is it? Well, this is a smaller problem, a problem of size n minus k, okay? And so I claim that we sum up, we break it all paths into where their first banging against the diagonal was. From there we count how many ways to get to that diagonal, how many ways to get from that. The product of those tells how many were in that class. Summing up over all classes, that tells me that there are this many different ballot sequences. Okay? This is exactly the recurrence for the Catalan numbers. Therefore, the nth Catalan numbers that path. Okay? Any questions about that? Okay? Good. Okay? Let's look at another problem. Okay? I give you now, okay, n rows of 2 boxes in a row. Okay, a 2 by n matrix. Okay, and suppose, let's say, I want to put the numbers 1 to 2 in, each number in one of those cells. Okay, such that each, such that every row, that both the rows are sorted and the columns are sorted. Okay, let's just make sure we understand this. For let's say that we have a problem of size 3. How many ways are there to put it like this, to fill these numbers in? For a problem of size 3. Okay? Does anybody see ways where you do it? One way you could do it, I guess, is you could put 1, 2, 3, 4, 5, 6, right? What's another way? And now all the rows and columns are sorted. Can someone give me a different one that all rows and columns are sorted? So I'm going to say 1, 2, 3, 4, 5, 6. All rows and columns are sorted, right? Any other ones or any other ideas? Okay. Is there some other way to do it? What if I put 1 and could I make 1 and 3 here? Let's say 1 and 2 here. Could I put 4 over here and finish the job? Yeah, I think so. I could put 3, 5, and 6. That would do it, right? Is there any other way I could do that? I could have, what if I had 1, 2, and 5? Could I finish that up? 3, 4, and 6. That's good. Could I put a 6 up there? No. Anything else I could do like this? Could I have a 1, 1, 3? Could I put anybody else up there? I could put a 4 up here, right? If I did that, then I'd have a 5 and a 6. No, a 2 and a 5 and a 6. Right? No, sorry about that. Right? Any other way I could do that? Okay. Could I start with a 1, 2, 5? A 1, 2, 6? No, that's not going to work. Okay. I don't think I can start with anything else, and I think I've gone through all of them. I claim that there are 5 of them. Okay. 5, does 5 sound like something? It is a Catalan number. Okay. Can anybody see why the number of ways to fill in this matrix might be, such that rows and columns are sorted, might be counted by the Catalan numbers? Okay. Let's think about this. Okay, any ideas?
Professor, because it divides things into 2 subsets?
Well, you're right, and I'm dividing it into 2 subsets, okay, such that they're sorted, but I don't, so you're, okay, what you're saying is, let's go a little further. Why are this divided into 2 subsets and interesting?
Because it's made out of 2n choose n. So it seems like one is twice the other subset. N is half of 2n.
Okay, what you're saying is that there's some connection to lattice paths here. That when we looked at the lattice paths, there were 2n. Here we had n. There were 2n things in the lattice paths, right? There were n steps to the left and n steps to the right. Okay? Now then, can we describe this in terms of steps on the lattice path? And I claim the answer is yes. Suppose we describe our legal path as we break our path into when did we make our moves to the left and the right. Let's interpret it like this. Here we've got this particular path. One way we could describe our thing here is to say, let's just say we went up to this point K. We could say that at the beginning we went left, then we went left, then we went left, then we went what? Up, then we went left, then we went up, 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 right? What if I now say 1, 2, 3, 4, 5, 6, 7, 8, and now build a matrix where I have the L's and the ups, and I write down when did I make my moves. 1, 2, 3, 5, 4, 6, 7, 8. I claim that this is going to be a legally sorted matrix. Why? Certainly, each row is going to be sorted. Why is each row going to be sorted? this is going to count the second step that I made to the left, and it says that happened after the first step I made to the left. Well, duh, that's right, okay? Why do I know that each column is going to be sorted? Okay? Is there any reason to believe that columns are going to be sorted? Okay? What does a column being sorted mean? What does it mean to say that I have the second, this here means that I had the second up move after I had the second left move. What does that mean? That means that
Below the diagonal.
means it's below the diagonal, right? So lo and behold, what I claim here is that the number of such ways to fill in the boxes is exactly equal to the number of ways to make paths across the diagonal that I don't get above it. Okay? And that is exactly counted by the Catalan numbers. Okay? Any questions? How many people believe this argument? Okay, good. Okay? So the Catalan numbers strike again. Let's get back to lattice paths. Suppose I have a matrix that is n by m. Okay? And I want to have a path that goes from here to there. I want to count how many ways is it possible to walk from here to there, shortest path possible. Okay? Ignoring the up or down constraint. How many ways are there across that lattice in this kind? Can anybody guess? Okay. Is it the Catalan numbers? Well, no, because it's counting things that aren't there. In fact, this, just to keep you alert, is the binomial coefficients. Why is there m? I claim it m plus n. Choose n ways to do this. Okay? Why is that true? Can anyone see why that's true? Okay. How many ways there are across how many different ways there are across an m by m lattice? Where I don't worry about going above the diagonal? Why are there n plus m, choose n ways of doing that? Okay, does anybody see it? You're saying that basically what I'm saying is every way of doing it, every path can be described as left, left, right, right, left, 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 right. Okay? That means that I can describe it as a path of length n plus m, right? This is, if I get across this thing, that means I have m left moves and n up moves and m left moves, right? So how many ways are there to do that? And the observation is that out of all possible ways, what I really need to do is to pick where did I make my left moves, right? We can just think that I have a total of n plus m steps. Okay? And really a way to describe a sequence is how many ways did I have to choose? Okay? My n left moves. Okay? My n up moves out of my total n plus m moves. How many people see this? This is one you should see. If you don't see it, let me know. How many people do not see why this is how many steps it is? A couple people. Good. Let's go through it one last time. So suppose, let's say I want to count how many ways there are across this particular lattice. Let's make it 2 by 3. Any way to do it is going to be some kind of, I'm going to have my trip from here to here will be described by 2 left moves and 3 up moves, right? Okay? So a way to describe it, all possible walks, if I told you, I gave you directions to get from here to there, I could do it using 5 steps, saying go left, go up, 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 left. Okay? How many ways are there to make 5 paths of left and up? 5 paths of length 5, just of length and left and up, ignoring where it goes. How many ways are there to do that? Okay? Well, I've got 2 choices for the first, right? 2 for the second, 2 for the third. There would be 2 to the 5th ways of doing that, right? Okay, but here I want very specific things. Okay, I want to know that all paths of length 5, such that I have 2 of them going to the left and 3 of them going up. One way that I could describe any such path is to tell you where were the lefts. If I said 1 and 3 were the spots of the lefts, you know that you could fill in the positions of the other 3, right? So my claim would be that it's the number of ways of choosing the lefts. There's going to be a total of n lefts from the total number of spots in here, which is the number of lefts plus the number of ups. Okay, and that's where it comes from. Any questions? Questions?
And Professor, using the same system, you could choose where your ups are.
So what?
N plus n, choose m is the same.
So what another argument says is that you're right. Instead of saying where did I choose my my left moves, I could choose my ups. Okay, maybe you're so conservative you don't want anything to do with the left. Okay, you want to choose the things going up. N plus m, choose m. Okay, but that's, of course, an identity we already know about. Okay, if you stop and think about it, you already knew that. That's just reflecting, exchanging things. Okay, any questions? Okay, so this counts the number of such lattice paths. Okay, any questions? Okay, good. Now, my claim is that I told you before that, so you should by now be starting to be convinced that these Catalan numbers come up a lot. Okay? And in fact, I'll show you some more of them. You probably are not so convinced that the nth Catalan number is 2n choose n times 1 over n plus 1. I showed you a hand-waving generating function thing, but you may be suspicious. This is such a nice expression that there should be a combinatorial way to prove it. Okay? And the way to prove it is a little bit, well, it's kind of interesting. Okay? Let's take a look at it. It's not that hard, but let's take a look at the following idea. Let's count how many sequences of 1s and minus 1s there are, such that we have a total of 2n plus 1 terms in our sequence. N of them are going to be 1, and n minus 1 of them are going to be minus 1. Okay? Suppose I give you a list of n plus 1, 2n plus 1 numbers, n of which are 1, the rest of which are n minus 1. And I add up all those numbers. What does my total come out to? 1, right? Does everybody agree with that? Okay, that's pretty simple. Okay? I claim that if I have a sequence like that, okay, one way I could construct such a sequence of 1s and minus 1s would be that I could construct a ballot sequence, okay, or one of these lattice paths, where every time I go left I have a 1, every time I go right I have a, every time I go up I have a minus 1. That would be one where I have n 1s and n minus 1s, right? If I add one more up, then I claim I've got such a sequence. Does everybody agree with that? That should be pretty clear. Okay? Now let's say I have a sequence of 1s like this. Any sequence of n plus 1 1s and n minus 1s. I claim there's an interesting property to these sequences. Namely, there is one way to circularly shift this sequence such that every prefix, if I take the sum of those numbers, is positive. Let's look at an example here. If I have the numbers, somebody tell me 1s and minus 1s. 1, somebody give me some numbers. Minus 1, minus 1, 1, minus 1, minus 1, 1. I need one more 1 than minus 1, right? So how many 1s do I need now? 2 more. Let's make it bingo. Okay, is that right? Let me shrink it so that we can see it clearly fits in here. So here I've got a sequence. My claim is that there is one way to shift. Let's call this number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I claim there is one way to shift this sequence. Circularly shift it. I mean, think of it as sort of tying the end around it. One starting point where all prefixes would sum to be positive. Prefixes meaning the beginning part of the sequence. Where is, for this particular example, that starting point? Does anyone see where that starting point is? Such that all prefixes are 1. That all prefixes would be positive. Does anyone? 7. So suppose we start at 7. That's where you want to break it. That means that we've got the sequence 1, 1, minus 1, 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1, right? Lo and behold, we've got a count of 1, 2, 1, 3, 4, 5, 4, 3, 4. Wait, what happened? Somewhere I lost somebody, right? 1, 2, 3, 4, 5. Right? 5 and, okay. So where did I lose this guy? I got 1, 1, minus 1, 1, 1, 1, minus 1, minus 1, 1, minus 1, minus 1. Yeah. Where did I make my mistake counting? At the beginning. Is this sequence right? Okay, good. So let me start counting. 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6. Where's my mistake?
You did 1, 1. Then when you did 1, 2, then you took away the 1 minus 1. You said 1, 2, 1, and then you said 3.
Okay, that I can't follow standing up here. I'm sorry about that.
Okay, in the beginning.
Okay. Okay, wait. Okay, now let me just add it up again. So the prefix here is 1. The prefix here totals to be 2. The prefix here totals to be 1. Prefix here totals to be 2, 3, 4, 3. I see. 2, 2, 3. Thank you. 2 and 1. Okay. Any questions? Okay. So this one is a legal way to do that, right? My claim is that every sequence of zeros and ones with this many zeros, this many ones and minus ones can be shifted exactly one way so it has that property. Okay? Let's say you believe me for now. Okay? I'll show you why in a second. Okay, but suppose you believe me. Okay, what do I now claim? Well, how many ways are there to pick out of 2n plus 1, either plus 1s and minus 1s? Exactly n plus 1, actually let's just take a look at this thing. N plus 1, 1 and n minus 1s. There's a space here that was lost, okay? How many ways are there to do that? Well, you choose the positions of the minus 1s. 2n plus 1, choose n. Does everybody agree with that? Okay. Now, how many of them, out of all these strings, how many of them have the positive prefix property? Okay. Well, my claim is that there are exactly 1 over 2n plus 1 of them that have the positive prefix property. Why is that? Well, out of all these distinct strings, we can break each set of strings into an equivalence class corresponding to the ones that get shifted to each other, right? So if I take all the strings of this type that consist of the right number of zeros and ones, I could break them into classes corresponding to what you get by circularly shifting them. Correct? Okay? How many people don't believe that? How many people don't believe that or are confused? Okay, some people. Okay? Let's break this into equivalence classes. Let's try for a small number. Let's say that for n, let's look at for n equals 2. What's 5 choose 2? Okay? What is 5 choose 2? Okay? 5 times 4 divided by 2, that's 10, right? Okay? What? How? What? 10, okay, sorry. Okay. How many such strings are there? I said that there's 10 ways to do it. What are those ways? Well, we could have, 1 minus 1, let's say 1, 1, minus 1, minus 1, minus 1. We could have 1 minus 1, 1. So I'm probably going to get myself in trouble doing this. Let's just take a look at one of these strings. Okay? 1, 1, minus 1, minus 1, 1. How many ways are there to circular shift that one? Well, if I circular shift it, I would also get what? 1 minus 1, minus 1, minus 1, 1, right? I would also get minus 1, minus 1, minus 1, 1, 1. I would also get minus 1, minus 1, 1, 1, minus 1. I would also get minus 1, 1, 1, minus 1, minus 1. And that's 5 of them, right? Okay. My claim is that I could break all these strings, and all of them have the same number of zeros and ones, right? Zeros and minus ones and ones, right? So I could partition all of those strings into equivalence classes based on circular shift. If what I said before, that only one of them has the prefix positive thing, then I claim that exactly this times 1 over 2n minus 1, okay, is going to be right, is going to be legal, correct? That's going to count how many such strings have this property. Now, what does it mean for a string to have this property of always being a prefix of positive 1? We could think of it as being, since we know it's always positive, the first step has to be a 1, right? Afterwards, we've got 2n numbers such that this guy never got to be, that the ones, the minus 1s never got ahead of the 1s, and they ended up tied. That is exactly the number of ballot sequences. That is exactly the number of Catalan numbers. So my claim is that you should believe is that the number of such strings of this type is equal to the Catalan numbers. That you should believe. You should also believe that, that this is a formula for counting that many. Okay? Correct? What I'd like to now claim is, let's say that we had, how does 2n choose n plus 1, 2n plus 1 choose n relate to 2n choose n? Remember, there was an identity here that we sort of showed. Okay? If not, let's look at it. Okay? Actually, my claim is this is equal to that. Actually, and suddenly I'm a little bit confused. Okay, my claim is that this is going to be equal to that, and that it can be shown by using one of these factoring identities out. Because here we're factoring out the term here. This claim is an identity. Okay? Maybe I should go and do that. Okay? Let's just see if we can prove that quickly. Suddenly forgot to do that step. Okay? Does anybody see how to prove that this is equal to that? Okay? Save me the effort of thinking. Simply expand it would be the way that I would do it. This is 2n plus 1 factorial over, son of a gun, we can get rid of that thing. Okay? This is going to be n factorial over what? N plus 1 factorial. Right? Okay? We could divide this by this. That's going to leave us with what? 2n. Okay? What if I now take this thing? What if I now pull out the n plus 1? Right? What gets left? 2n over n factorial, n factorial. And what is that? 2n choose n. Okay? So lo and behold, this is equal to exactly what I say, okay, the Catalan numbers are. Okay? And that, I claim, completes the proof if you believe this circular shift property? Okay? How many people believe the proof if you believe the circular shift property? Okay? How many people don't believe it or want to have any questions? Okay? But why does the circular shift property hold? Let's stop and think about that. What was the circular shift property? The claim was that any appropriately numbered sequence of numbers has exactly one all positive shift. Okay? This is not in the notes, but let me just use this as a way to prove it. Let me first convince you that any sequence of n plus 1 ones and n minus ones must have at least one such shift. Okay? How do I do it? Let's say I take your input sequence. Let's zoom this baby up. I take your input sequence, 1 minus 1 minus 1, 1, and draw a line every time I have a separator between a minus, at the end of a string of minus 1s, possibly empty, before every 1. Let me draw a line. Okay? Now certainly, if I'm going to have a sequence of all positive prefixes, it's got to start with a 1. Does everybody agree with that? Yeah, that seems pretty clear. So let me think about it. Suppose I start out here, okay, and you give me your original sequence. I shift it till the first block comes into place. So it starts with a 1. One of two things could happen. It could either all have positive prefixes, in which case I'm done, or there's going to be a negative prefix, correct? Suppose, oops, here is a negative prefix. Suppose I now put that block at the end of this thing. 1 minus 1 minus 1 minus 1 minus 1, 1, 1, 1, and move this guy to the end. Are these guys now going to be happy? Okay. Well, we know that above it, if you could get through all of these guys with a positive prefix, this is not going to be a problem. Why? Because we know there have to be more 1s than there are 0s, right? Negative 1s. If there had to be more 1s, they weren't back here, were they? They had to be up here. So if this thing all had positive prefixes, then we know that these guys would be happy, right? I claim we can keep finding, if anybody is unhappy, the zone of unhappiness has to keep getting smaller and smaller each time we push another one of these blocks back. Okay? And if it gets small enough, eventually it goes to 0. Okay? So I claim that by doing this operation, okay, if there is, okay, there has to be at least one solution that I'm going to find. Okay? How many people find that convincing? How many people don't find that convincing? Okay? Most of you find that convincing. Good. I now claim that any sequence of n plus 1 1s and n minus 1s can only have one such sequence of positive shifts. Why? What would be the general strategy you would want to do to prove this? Does anybody just think a little bit about proof strategy? If I were to say prove that any such sequence has only one such shift, how would you prove it? Well, it would be by contradiction. Okay? Suppose not. That means that there's got to be at least two, okay, such starting points, right? And you're going to tell me, look, okay, that means that here is starting point number 1, here is starting point number 2, right? Well, let's think about it. If this is a starting point, this means that every prefix from here on is positive, right? So what is the sum from here to the end of the string? Okay? What do we know about this? It's got to be greater than 1, right? Greater than or equal to 1. Okay? Here's the other starting point. Every prefix has to be positive. What's the sum from here to here? Well, it's got to be, all the strings have to be, it's the whole string. It's got to have 1 here. Okay? What is the sum from here to here? Well, we know that it is got to be positive because this is a legal starting point, right? And we also know that it's got to be 1 minus this, right? Okay? But what is this? Okay? This is greater than 1. So 1 minus something that's greater than or equal to 1 has got to be less than or equal to 0. And therefore, this cannot be a prefix sum. Okay? How many people get the idea of the proof by contradiction? How many people don't get it? Okay? Good. Okay? And so, lo and behold, I claim that this proves that the Catalan numbers have to be counted by this kind of a sequence. Okay? Not a trivial proof to have come up with. I'll give you that much. But I think it's one that's quite understandable. Okay? And does, again, illustrate our counting methods again. Any questions? Okay? Good. Let me show you one other counting problem that may be a interesting thing. How many ways are there to triangulate a convex polygon? What do I mean by triangulate it? I mean to partition it into, here is a polygon of size 5. That means to sort of add edges into the interior. Here we had points 1, 2, 3, 4, and 5. Add points into the interior such that the whole interior is carved into triangles. Okay? Triangulation is an important operation in graphics and geometry, and it's a good thing to read can be done. How many, let's take a look at this thing. How many different ways could a polygon on 5 vertices like this be triangulated? Okay? Can anyone look at this and make an idea? Is there any way that we could do it with one edge from 4? Okay? Let's say that here we have 2 internal edges from vertex 1. Is there a way we could do it so that there's one internal edge from vertex 1? Can anybody find a triangulation to do that? Saying you want to have this one go away and do that, right? That's what you're sort of saying. In general, I claim that there are 2 ways to triangulate 4 points. Okay, right? You could put the middle divider anyways. There's only 2 possible switches. In a 5-vertex polygon, I claim actually that there's exactly 5 ways to do it. Okay? And a good way to think about that is to say, well, look, in any such triangulation, there's going to be one internal vertex here of degree 4. Okay? And in fact, we could pick any one of those to be the, that vertex. 3 of the 5 choices would do. Okay? But it looks like somehow it's so constrained when you only got 5 points that you have to have any such thing. Okay? Any questions? Okay? 2, 4. Does anyone want to guess how many ways, what do you want? 6 points can be triangulated. Okay? Okay? Some people I see are thumbing back to their table of the Catalan numbers. 14. Okay? Can anybody see why this is counted by the Catalan numbers? Okay? Let's think about this. If you want to see why, somehow you should be exploiting the recurrence relation, right? That's what defines the Catalan numbers. Why does that recurrence come up here? Well, my claim is if we have a big polygon here, here's our polygon. Actually, it's not a good one. Let's just another piece of paper on it. One, 2, 3, 4, 5, 6, 7. Here's vertex 1 and vertex 0. is this edge going to be involved in a triangle, in the triangulation? Okay, well, it's got to be, right? Because everything's got to be carved up. Okay? If it's going to be involved in a triangle, how many vertices does a triangle have? Well, 3. Here we've got 2 of them, right? So I claim that there's got to be, in this triangulation, it's going to be connected to some vertex k, right? Okay? Now, how many steps are needed to complete the triangulation? Okay? Well, here we've got how many vertices? Okay? Well, if here we had 1, 2, 3, 4, 5, this was counting a problem of size k, this is now a problem of size k minus 1, right? And how big is this problem? Well, this problem is going to be something like n minus k. You got to get your indices right. Okay? But you should see that the heart of this thing is that if we have n points numbered from 0 to n minus 1, that's n points. We have 0, 1 connected to k. What gets left is, okay, on this side, we've got how many points? We've got a problem now. We have thrown out, okay, I believe n minus k points. Right, here we had this is a problem you can think of as a problem. Here we were numbering from 0 to n minus 1. If we number this as 0, that would be k minus 1, right? So this is a problem of size k here. How big is the other problem? Well, here we have a total. Okay. Here we have a problem of counting from k to 0. K to n minus 1. How many points is that? Okay. Well, that's okay, I think it's n minus 1 minus k plus 1 n minus k. Okay? You have to, again, check the indices. But basically, you've got a Catalan-like recurrence. Okay? And lo and behold, it's the same recurrence. The indices may be disguised. Okay? But you normalize the indices, you get the exact same thing. Okay? The number of triangulations is counted by the Catalan numbers. The only thing that's different, actually, is we have an example where the starting point shifted. Because how many ways are there to triangulate 3 points? Well, there's 1. It's already done. So instead of the number of triangulations being the Catalan numbers, I think it's going to be C of... the number of triangulations on n points is going to be C of n minus 2. Okay? But basically, it's the same thing. Any questions? Okay? So look for convolutions. Okay? They're things that are not that hard to see. Okay? They come out a lot in combinatorial problems. Okay? And it just gives you another tool to think about things. Any questions? Okay. Why don't we, I had some other stuff I wanted to do, but it's close enough to the end. Think about the Catalan numbers, respect them, and get going on the homework, and I'll see you guys next class. Okay, thanks a lot. Yes?